Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comsets University, Islamabad WA campus. The slides used in this lecture have been edited from multiple sources, including the two sources given on the screen. The topic that I'm going to discuss in this lecture is the hardware specification or external pin configuration of the microprocessor 8086 and 8088 microprocessors. So the external pins of the and their functions of the pins used in 8086 and 8088 microprocessor will be discussed in this lecture. This is the functional blocks of the typical microprocessor. The first block is the computational unit of the microprocessor, that is called the arithmetic and logic unit of Intel microprocessor. This block is, as the name indicates, is arithmetic and logic unit that is responsible to perform arithmetic and logic operations on the data. And the arithmetic and logic operation is encoded or told to the microprocessor through the instruction sets or instructions of the instruction set of the Intel microprocessor. There is a flag register, normally called flags or E-flags in the modern microprocessors. Flag register stores various conditions of the results. So the conditions are stored as status bits called flags in the flag register. So for example, the carry flag or the overflow flag or the parity flag or the direction flag, these are the flag bits that stores the status after the computation, arithmetic and logic operation. To store result and data, there is a setup or array of internal registers in the microprocessor. The number and the sizes of these registers vary from member to member in the Intel family. There is normally a program counter or sometime instruction pointer register. So the purpose of either of these registers is the same. An instruction pointer generates the address of the instructions to be fetched from the memory, and the address of that instruction is sent through the address bus. So the instruction pointer stores a 16-bit address or the offset address of the instruction that will be executed next. So after the current instruction is being executed, the microprocessor maintains or stores the address of the next instruction in this register. So together with the code segment, this register provides the physical address or the memory address of the instruction that would be executed next. Then there is an instruction decoding unit. This instruction decodes the operation to be performed by the instruction and sends information to the timing and control unit. And then the timing and control unit is responsible to generate control signals for internal and external operations of the microprocessor. These control signals are generated as a result of interpreting the operation code of the instruction. This is a family member, a popular member of the Intel family of microprocessor called 8086 microprocessor. This microprocessor, 8086 microprocessor, is packaged in the dual inline packaging, where both sides of the microprocessor has external and internal pins, input and output pins. 8086 is packaged in the form of 40 pins, where 20 pins are arranged in the left side and 20 pins are arranged on the right side of the microprocessor. Some of the pins have different functions. They are called multiplex pins, and some of the pins are used in some of the pins have different functions when they are used in the minimum mode or in the maximum mode. For example, FEN24 till FEN31 have these functions when they are used in the maximum mode. So these are the maximum mode pins. These pins function differently when they are used in the maximum mode. In the maximum mode, the microprocessor is connected with a coprocessor. So these pins are used for a different purpose when they are used when the microprocessor is operating in the minimum mode. So when the microprocessor is operating in the minimum mode, FEN24 till 31 would have these functions. And all of the rest of the fins are common in both modes. So microprocessor is operating in two different modes, minimum mode and maximum mode. In the minimum mode, microprocessor is generating all of the control signals in itself, while in the maximum mode, there is a controller that generates signals, and the microprocessor can be connected with the coprocessor. So it's in the maximum mode, microprocessor is operating in a multiprocessor environment. Here are some major differences between 8086 and 8088 microprocessor. Both of these microprocessors are used in the general purpose computer, and both of these microprocessors are 16-bit microprocessors. So the data bus by 16-bit microprocessor, we mean that the internal registers are 16-bit wide, but still the data bus in both of these microprocessors is different. So the data bus is of 16 bits in the 8086 microprocessor, while the data bus is of 8 bits in the 8088 microprocessor. In 8086 has 3 available clock speeds. It can work at 5 MHz, it can work at 8 MHz and 10 MHz, while 8088 microprocessor has 2 available clock speeds, 5 MHz and 8 MHz. 8086 microprocessor has a memory control fin designated with MIO, or where there is a bar on the IO. So this is designated with MIO signal, while in the 8088 microprocessor this has a complementary memory control pin, which is IOM signal. So IO comes first and M comes later, and it has a bank high enable signal. 8086 has a bank high enable signal or bus high enable signal, while it has status signal SSO. This signal is required to enable the high bank of memory, because it can access 16-bit of data at the same time, and such pin is not needed in 8088 microprocessor because it can access only 8-bit of data at the same time, because the data bus is 8-bit wide. It can read or write 8-bit or 16-bit word at the same time, because we have the 16-bit data bus in the 8086. It can read only 8-bit word at the same time, because the data bus is of 8-bit, so it can only read 8-bit word at the same time. Here the two microprocessor 8086 and 8088 microprocessor are given with the fin configuration of both of the microprocessors. Most of the fins are similar, just they are arranged or on different locations, or on their functionality. Their fins are location of their fin is slightly different, but most of the fins are located in the same position of the microprocessor, and they have the same function in both of the microprocessor. But some of the fins are different. Here on the 8088, these fins are multiplexed. Only 8-bit 8 fins of the microprocessor are multiplexed for the address and data. So 80 till 87, these fins are multiplexed for the address as well as for the data. So these fins can be used for sending or receiving data, as well as for sending the address of the memory location or the input and output port. So these 8 fins are multiplexed for data and address, while in case of 8086 microprocessor, 16 pins are multiplexed for data and address. So AD0 tell AD14 on one side and then AD15. So these 16 pins are multiplexed for data and address. Because the data bus is 8-bit wide in 8088, so that's why only 8 data pins are required. So that's why the rest of the address pins are not multiplexed for data. While in case of 8086, the data bus is 16-bit wide. It can read 16-bit data at the same time, so that's why 16 data pins are required. So they are multiplexed or for the address pins. So these 16 pins are used for two purposes. They can be used for the address, for sending the address of data, and they can also be used for sending or receiving 16-bit data. So 16 pins are multiplexed for data and address, while here only 8 pins are multiplexed for data and address. The second difference between the two microprocessors in terms of the fins is that fin 28 is IOM, while here the fin 28 is MIO. So that is only the difference of the labeling. So for example, when this fin is 1, then the IO input and output devices are accessed. And when this fin is 1, then the memory is accessed. So, and when this pin is 0, then the memory is accessed, while when this pin is 0, the input and output devices are accessed. So that is the difference between the two in terms of this pin. And a third difference is that fin 34 is status signal 0, while fin 34 in 8086 is bus high enable, or it is multiplexed with status 7. So bus high enable is or bank high enable function is needed in 8086 microprocessor because sometime 8-bit of data is retrieved or written, while sometimes 16-bit data is accessed. So in case of 16-bit data, when 16-bit data is accessed, the high part of the bank or the high part of the 16-bit data should be enabled, and that is done with this pen. Here we have the block diagrams of the minimum mode of 8086 and 8088 microprocessor. So here we can see how the 8086 and 8088 microprocessor are interfaced with the external environment. So the control signals in both of these microprocessors are generated by the microprocessor themselves, and here we can also see the major differences between the two in 8086 and in 8088 microprocessor. So most of the pins are same, but here we have the differences. So the address bus or the data bus is different than the address or data bus of the 8088 microprocessor. So here we can see that the pins or the lines AD0 till AD15 are multiplexed for data and address, while in case of 8088 microprocessor, these are not multiplexed. The pins A8 till A15 are not multiplexed with data. They are simply used for the address, for the high 8-bit address. Only AD0 till AD7 are multiplexed, while the rest of multiplexing is the same in both of the microprocessor. So the address and data bus multiplexing is different in both of these microprocessors. So here the 16-bit address and data are multiplexed, and here only the 8-bit address and data are multiplexed. So 8 till A15 in the 8088 microprocessor is not multiplexed with data. So these pins are only used for the address transmission. Another difference between the two microprocessors is, as I said on the earlier slides, is the bus high enable or bank high enable pin. In 8086 we have the bus high enable pin, and status is 7. These two are multiplexed on this pin, while on the 8088 microprocessor we have the SSO pin, and there is no need of the bus high enable or bank high enable pin. The third difference is the MIO, where this pin is sending a signal to access the memory or the input and output devices, and the memory is accessed when a 1 is sent through this pin, while in case of 8088 it is IOM prime, so the memory is accessed when a 0 is sent through this pin. Minimum mode interface of 8088 microprocessor. In the minimum mode, microprocessor is, as I said, the control signals are generated by the microprocessor itself. So microprocessor provides all of the interface signals in itself. The address and data bus signals are provided by the microprocessor. The status signal, or for example S0 till S7, are provided by the microprocessor. Control signal, for example reading and writing control signals, are provided by the microprocessor itself. The interrupt signal are received or provided by, for example, hold, acknowledge, interrupt request, NMI, and interrupt acknowledge. These signals are provided by the microprocessor itself. And control signal related to the direct memory access, which is represented with DMA, for example hold and hold acknowledge. These signals are also generated by the microprocessor itself. Multiplex, there are some multiplexed address and data bus fins on the microprocessor. The 20-bit address in the 8088 microprocessor is multiplexed. These 20-bit address pins, that is representing the address A0 till A19, the 20-bit address, and this 20-bit address in the 8088 and the 8086 microprocessor is sufficient to provide 1 megabyte of the address space. So 1 megabyte of memory can be addressed. 8-bit data bus, D0 till D7, and this data bus is multiplexed with the first 8-bit of the address. Signals of the address data bus, it has both of these multiplexed address data multiplexed pins provide signals for the address and data bus. AD0 till AD7, these pins are multiplexed and they are bidirectional. They can be used for the lower 8 address output lines, and they are also used for 8 bidirectional data bus lines. So these pins are used to receive the data from the memory or the input and output devices, or these pins may also be used to send data to the input and output devices or to the memory. So they are bidirectional data bus, connected to bidirectional data bus, as well as these pins are used for sending the 8-bit lower 8 bits of the 20-bit address. A8 till A15 in 8088 are not multiplexed. They are output pins only, while these pins are bidirectional. But the A8 till A15 pins are only used for the output to send the next 8 address lines or next 8 address bits of the 20-bit address. The last 4 bits of the address, A16 till A19, are multiplexed with the status pins S3 and S6. These are output pins. They provide the 4 most significant address lines of the 20-bit address, 20-bit address of the 8088 microprocessor, and these pins are also used for providing the 4 status signals S3 till S6. For the memory and input and output, there are a number of control signals. They are generated by the microprocessor. So it supports signals for controlling the memory and input and output I/O interface circuitry. So all our output signals except the ready signal, which can also be as which is an input signal, but most of all the rest of the control signals are the output signals. One of the control signal is ALE, which is address latch enable, and this signal is used to control the external circuitry, for example buffers and transceivers, that a valid address is on the address bus and it should be latched So this controls the external circuitry or buffers or transceivers to enable the address that it is used in demultiplexing the address in data pins. Then there is an IOM or input and output devices or the memory pin. This pin designates or identifies type of data transfer taking place over the data bus. When the data is being sent or received over the data bus, this pin tells if the memory is being accessed or if the input and output devices are being accessed. It is used to enable or disable memory and or input and output interface. So again, this pin is connected with external circuitry that controls if the memory is being accessed or if the input and output devices are accessed. When the input and output and memory pin is 1, this would signal that the input and output devices are accessed. And when the input and output and memory pin is 0, then this would signal that the memory is being accessed. Similarly, then there is another control signal called data transmit and receive. So it is used for if the data is being transmitted or sent, or if the data is being received from the external memory and input and output devices. So it tells the external circuitry. Again, the circuitry can be transceivers, bidirectional transceivers, or unidirectional buffers, which so tells the external circuitry which way data is to be transferred over the bus, used to set direction of the data bus interface circuits. So when the data is being transmitted for writing to the input and output devices or to writing to the memory location, then data transmit and receive pin is set to 1. So that would signal that the transmit is happening, or the write operation is happening. And when the data transmit and receive pin is 0, so this would signal that the read operation is currently happening. So when the data is being read from the memory location or it is read from the input and output device, then this is indicated through this data transmitter and receive pin when this is set to 0. So these pins, this pin is also used for controlling the transceivers to set the direction of the data, whether it is going outside of the microprocessor or it is coming inside of the microprocessor. Then there are other memory and I/O control signals. Read signal is read active. It is active 0, and it signals that a read input and input or read or input bus cycle is in progress. So when this signal is 0, this signals the external devices that a read operation is currently being held. So the data is being read from the input and output devices or from the memory location. And whether it is memory location or input and output device, that is decided by the input IOM pin. Then there is another control signal called the write strobe. The write strobe or the write pin is active 0, and it signals that a write or output bus cycle is in progress. That means that the data is being written to a memory location or to an input and output device. The other control signal data DEN, that means the data enable, which is active 0. So this enables the data address. It signals when the data bus should be enabled. So for example, when the multiplex address data bus is used for sending the data, then this pin is used. So when this pin is 0, it would enable the data address bus. Ready pin is the only input control signal and the memory and I/O control signals. This pin is used to acknowledge that the memory subsystem is ready to complete the bus cycle. So when the ready pin is 1, it acknowledges that the memory subsystem is ready to complete the bus cycle. And when it is 0, the memory system is not ready. So the microprocessor has to wait. So it inserts wait states to extend the bus cycle because the memory system still needs the bus. And the last memory I/O control signal is status signal. That means that when it is 0, it means that instruction code is being read, and when it is 1, that means that the data is being accessed. Apart from input and output and memory control signals, there are interrupt signals as well, interrupt interface as well. So it supports signals for implementing an interrupt-driven input and output interface, or the interrupt-driven input and output mechanism. A microprocessor sends a request or sends a command to the input and output devices to perform input and output operation. And then after the input and output device is ready to perform that operation, it signals the microprocessor that the assigned task has been completed. So in this format, or in this technique, the microprocessor is always busy to execute an instruction, and it is not waiting for the slow devices. So it enhances the performance of the microprocessor. So it has two types of interrupt pins. One is maskable interrupt interface, that is interrupt request pin, or INTR. So and then there is an interrupt acknowledge pin. So the interrupt request pin is an input pin through which interrupt request is received, and interrupt acknowledges the interrupt. And then there is a non-maskable interrupt interface as well, and that is represented with NMI. That means non-maskable interrupt. So through this pin, interrupt requests are still received, and the interrupt request cannot be disabled. So that's why they are called non-maskable interrupts. And then there is a reset interface through which reset pin that is used to reset the microprocessor. So interrupt request input is active 1, and it is level triggered. So external devices can signal through this pin that the microprocessor that it needs maskable interrupt service. So whenever an external device needs to interrupt the activities of the microprocessor, that device then sends a 1 through this pin that would signal the microprocessor that a device needs the attention of the microprocessor. And then microprocessor can acknowledge that interrupt through the interrupt acknowledge output, which is active 0. So when a 0 is sent through this pin, microprocessor acknowledges to an external device that its maskable interrupt request is being serviced. And when this is happening, when a request is received and when an acknowledge is sent to the device, the microprocessor enters into an interrupt cycle, and an interrupt service routine or interrupt service provider or an interrupt handler is then executed to address or to respond to that interrupt. NMI is non-maskable interrupt input. External devices initiates NMI request with 0 or 1 transition, 0 to 1 transition, and that is called edge triggered transition when the signal is transferring or transition from 0 to 1. The difference of NMI is that this interrupt cannot be disabled through the interrupt flag. Reset is a reset input. It is active 1, and when it is logic 1, it initiates hardware reset of the microprocessor, and when initializes internal registers and reset service routine. So the execution stops and everything is reset. So the microprocessor is reset to its initial state. There are direct memory access interface. There is a direct memory access interface as well when the external DMA controller wants to request the microprocessor for a DMA access. Then there are 2 fins used for this purpose. It supports signals for implementing a direct memory access interface. It permits or allows direct transfer of information between different locations of the memory or between memory and input and output devices. So in DMA mechanism, input and output devices and memory can share data with each other without passing the data through the microprocessor. So external devices such as a DMA controller perform these operations independent of the microprocessor. but still this operation needs to get access to the master bus or to the bus system or to the system bus, and this request is sent to the microprocessor through the hold pin. So hold request input active one, it is level triggered. External device or the DMA controller requests the microprocessor to give it the control of the system bus, so that the system bus is used for the direct memory transfer whenever the input and output device and the memory needs to transfer data between them without passing independent of the microprocessor, without passing the data through the microprocessor. So when the microprocessor, the DMA controller requests the microprocessor through the hold pin, if the microprocessor is swelling, it acknowledges through the hold pin, hold acknowledge output active. So it acknowledges to an external device controller, which is DMA controller, that the microprocessor bus is in the hold state, that it can be used. Minimum mode of the 8086 microprocessor, data bus is 16-bit wide in the minimum mode, even in this is 16-bit wide in the maximum mode as well. The data bus is D0 till D15, so these are the 16 bits of the data bus. These 16 bits are multiplexed with A0 till A15 of the address bus. So these 16 bits are used for data as well as for address, while the rest of bits of the address are multiplexed with status. So it allows the 16-bit data bus allows 3 types of data transfers. It can transfer a word of data at the same time, and for that the pins D0 till D15 would be used to transfer, to read or write 16-bit of data, that is a word. The same 16-bit or 16 pins may be used for the low byte transfer, and for that purpose pins D0 till D7 would be used. The low byte or the lower byte data or the lower byte pins or the lower 8 pins may be used for this transfer to send or receive a low byte of the word. And if only the high byte of the word needs to be read or written to any location or any device, then D8 till D15 are used. Memory and input and output controls is the bus high enable or bang high enable is the pin for memory and input and output control. This bang high enable pin is used to signal external circuitry whether or not a byte transfer is taking place over the upper 8-bit 8 data bus lines. Whenever the 16-bit data is being accessed, or whether the upper byte of the word is being accessed, then the upper or the higher bank should be enabled, and for that purpose this bus high enable bank high enable or bus high enable pin is used, and this pin is connected with the external circuitry to control the access of the upper 8 bits of the 16-bit data. The maximum mode interface is 8088. In maximum mode, microprocessor unit doesn't directly provide all the signals, while we just saw that in the minimum mode, 8086 and 8088 microprocessor are generating all of the control signals, while in case of the maximum mode, 8086 and 8088 microprocessor are not generating all of the control signals. Control signals, for example, write, IOM, data transmit and receive, data address enable, address latch enable, and interrupt acknowledge signals are no longer provided by the 8088 microprocessor, and instead these control signals are generated by a controller. So 3 signal lines, S0, S1, and S2 identifies which type of the bus cycle is to follow. For example, whether it is a memory read cycle, memory write cycle, or advanced memory write command. So for this, maximum mode signals are these are the maximum mode signals, and maximum mode signals are achieved when the maximum pin is connected to the ground. So when it is connected to the ground, maximum mode is achieved. And in this mode, the two pins request and grant pins, request 0, request 1, or grant 0, grant 1. These are the two bidirectional pins to request the bus, or the same two pins may be used to acknowledge if the bus has been granted. Then there is a pin lock that bus priority lock control. It locks the bus, the master bus. And then there are three status pins, S0, S1, and S2. They generate the bus cycles or the external control signals. And the two key pins, key status 1, key status 0. So these two pins indicates the status of the internal instruction key. And the values or the possibilities or the cases of these two pins are interpreted as on the right side. So there are four possibilities: 0, 0, no operation on the key; 0, 1, that means the first byte of the opcode is accessed from the key is empty, or the bytes are accessed in a sequential pattern. Similarly, the three status pins S0, S1, and S2 of the microprocessor are interpreted as given in the table. So there are 8 possibilities in the control signals are generated by a controller called 8288 controller or bus controller, and this controller generates these signals for either of the 8 possibilities of the status signals: interrupt, acknowledge, read input and output port, hot, write input and output port, instruction, read memory, write memory, and passive. In the maximum mode, memory control signals are here. They are given as the block diagram, and the microprocessor considered here is the 8088 microprocessor. So we have the 8088 microprocessor, and the minimum mode and the maximum mode pin of the 8088 microprocessor is connected with ground, and when it is connected with ground, that would choose the maximum mode of the microprocessor. And as I said earlier, in the maximum mode of the microprocessor, the 3 status pins S0, S1, and S2 are connected with a bus controller 8288. This is a bus controller, and this bus controller, just like the microprocessor, is getting a clock signal to synchronize the activities of this controller. And in response, this controller is generating the control signals for the memory and input and output devices. So these are the control signals, and together with these control signals and the address and data bus. So the address and the data bus is connected with the address and data pins. These 8 pins are multiplexed AD0 till AD7 in the 8088 microprocessor, while these pins are not multiplexed A8 till A19. And these control signals, address pins and data pins, are connected with the memory subsystem and the bus interface circuitry. There are a number of other interface circuitry like buffers and transceivers and memory systems, and all of them are used to generate the address, data bus, and control bus to control the memory and the input and output devices. In 8086 and 8088 microprocessor, when they are operating the maximum mode, the 8288 bus controller can be connected as the following. So here we have the 8086 microprocessor, and here we have the 8088 microprocessor. Both of the microprocessors are connected with the 8288 bus controller, and this bus controller is connected with the microprocessor when the microprocessor is operating in a multiprocessor environment. In this environment, microprocessor is not generating all of the signals, and instead there is a bus controller that generates the input and output and memory control signals. So these are the control signals generated by the 8288 bus controller in case of it is connected with 8086 microprocessor, and these are the control signals generated by the same controller when it is connected to 8088 microprocessor unit. There are some other differences we have all mentioned earlier. The address and the data bus are multiplexed, but in 8086 AD0 till AD15 are multiplexed for the address and data, while in case of 8088 microprocessor, only AD0 till AD7 are multiplexed, while A8 till A15 are not multiplexed with data. So these address bits are provided through the A8 till A15 address pins of the microprocessor, 8088 microprocessor. And here we have the interfacing of the clock generator with 8086 microprocessor or 8088 microprocessor. Here we have an 8086 or 8088 microprocessor, and the clock pin, which is there to receive the clock signal, and this signal is received from an external clock generator. This clock generator is called 8284A. This clock generator generates the clock signal, and that clock signal is then connected with the clock pin, which is the input pin of the microprocessor, as well as the reset pin of the 8284A. Clock generator is connected with the reset pin of the microprocessor. So this is the external clock generator that generates the main clock signal to synchronize the activities of the Intel microprocessor 8086 and 8088 microprocessor. Thank you.